All right, well, welcome everyone to our Radio Shop chat organized by SpectrumX, the National Science Foundation Spectrum Innovation Center. My name is Nick Lanneman. I'm professor of electrical engineering at Notre Dame, and I'm center director for SpectrumX. I'll hand things off to my colleague, Monisha Ghosh, here in a minute to introduce today's speaker. First, let me remind everyone that SpectrumX is the world's largest academic hub through which all radio spectrum stakeholders can collaborate and innovate to make the best use of this precious resource to benefit society. Second, the purpose of our Radio Shop Chat series is to bring the community together to educate, perhaps debate, and inspire some next steps in collaborative research, workforce development, and policy outreach in this area. Third, our Radio Shop Chats follow the Chatham House rule, which means that participants are free to use the information that they receive, but neither the identity nor the affiliation of the speakers nor that of any other participant may be revealed without their permission. So thank you for participating. We hope you enjoy this chat, and please spread the word and offer suggestions on additional follow-up chats that we might organize. With that, let me hand it off to Monisha.
Thank you, Nick, and welcome everybody. It's my real pleasure to welcome Roger Nichols to the Radio Shop chat. Roger has 37 years of engineering and management experience in wireless design and measurement at HP, Agilent, and Keysight, and his roles have spanned R&D, marketing, and manufacturing. He has managed projects, programs, and departments beginning with analog cellular radio and on every subsequent standard evolving to 6G. He directed Keysight's 5G program starting in 2014 and Keysight's 6G program starting in 2019, when I guess 5G was barely getting deployed. He's also the director of Keysight's work in wireless standards. And most importantly, Roger holds a BS from the University of Colorado Boulder, which is one of the founding institutes of SpectrumX. So with that, I'll hand it over to Roger. Many of you who know of him have met him in his capacity as Advanced Networking Program Manager of Keysight. So over to you, Roger.
Okay, can you see my screen? My
Yes.
slides?
Yeah.
Excellent, thank you so much. Thanks for the introduction, and it's an honor and pleasure to speak in front of you folks. I think
Oh, we're on the other side.
we've got a little bit of background noise there, but I'll carry on here. Monisha asked me to come speak based on some news that got out about us with Spectrum Horizons licenses from the FCC for investigation in the territory north of 270 gigahertz. And so I know there was some questions about that. I'll probably spend less time talking about that and more time talking about in general where this is headed, and particularly from a measurement perspective, because it's really mostly what I'm qualified to do based on my experience. So what I'll cover is some of the drivers. I know most of you are aware of those, but I'll highlight a couple of specifics. Some perspective on how we think of what happens when spectrum is added and what we have to deal with, and what some of the major issues are for these higher frequencies. And then just a few thoughts on coexistence and a quick conclusion. The one thing I want to highlight too is that I am the 6G program manager, and like the rest of you, it frustrates me when people think of 6G as being about sub-terahertz, because that's only one of the technical areas that's being explored and researched. There's plenty more, and without all of them working together, the system is not going to fly. But this discussion will be primarily focused on that, on the spectrum issue. And I will use the term sub-terahertz to refer to everything from 100 gigahertz to 1 terahertz. That's just nomenclature for what I'm going to say today. So forgive me, it's my shorthand for the terminology. There's a long debate on what we should call this, but that's just what I'm going to use today for this area. So from the standpoint of history, just to look back a little bit, that band right there that I've circled is what is particularly relevant to big, wide-scale mobile commercial communications right now, and to get an idea of how we're messing around with spectrum and what we're doing here. You know, I have a logarithmic scale and a linear scale, and the amount of spectrum that was set aside for the first generation is mapped there. And in the linear scale, I think I made that 1 pixel wide. So it's a pretty small linear scale. And even 2G and 3G did not add too much to that, although practically, well, much more than doubled it. But it doesn't seem super huge on the linear scale until we added all the extra bands for the 4th generation in LTE, and then 5G is when we stepped into what people call the millimeter wave, so between 24 and now 71 gigahertz. And so the linear bar got quite a bit bigger, and obviously you can see how much of the logarithmic space gets occupied. And potentially there's more to come in the area between 7 and 20 gigahertz. There's a lot of talk about that, but I haven't mapped that in there yet. But to give some perspective, not counting the bands below 20 gigahertz that are potentially going to be considered for 6G, if we just think about this sub-terahertz region, it gets pretty big. And that's evident in both of the scales here, but you get an idea of what is being considered. And a little bit of history, you can see we've kind of moved from analog voice to smart networks and adding a tremendous amount of spectrum. So why? Well, the growth really comes from, it's a little bit tongue in cheek here, but it comes from a tremendous amount of penetration of the smartphone and the use and performance. So you've got screen resolution and data rate that have gone significantly higher in the last decade or so, and a tremendous amount of growth in video applications, which video is now way more than half of all the mobile data used around the world. Now, I stole this graph from the Ericsson Mobility Report, and just to illustrate 2 things here. Number one, we are almost at a global use of 100 exabytes per month worldwide mobile data, uplink plus downlink. And that growth rate has been higher than 35% since 2014. In fact, in most of the years, a lot higher than that. So those are tremendous numbers. 100 exabytes a month is, exabyte is 10 to the 18th. 100 exabytes a month is, I think, 150 billion 64 gigabyte thumb drives, which would go around the world, I think, 1 1/3 times if you lined them all up. So the numbers are staggering. The scale is actually a bit difficult to comprehend, especially when you look at spectral efficiency, which I maintain we haven't really done much to improve in terms of bits per second per hertz. What we have done is improve spectral efficiency on a per square meter basis or per square kilometer basis by making the cell size smaller. But with all of the effort put into signaling and coding and complex modulation, our spectral efficiency hasn't made a lot of growth. So why are we going to keep going with this with 6G? The smartphone penetration is certainly not going to grow like it did. Well, there will be applications that demand more. Are we going to have holographic telepresence with tactile interaction? I don't know. But just as an illustration of one of the applications that's being considered, if you think about all the things that contribute to the amount of data rate or the data rate that's required, and this doesn't count all the other things you have to get to work for holographic communications, how many pixels, what's the block size of the hologram, the color depth, frames per second, and then work you have to do to get rid of artifacts like speckle in holograms. The size of the object makes pretty big difference. If you look at 5 centimeters, based on the research paper I have here, it's about 10 gigabits per second, given all those other figures of merit there. But something the size of myself, quite possibly a significantly higher at perhaps a terabit per second. So those numbers are a little bit staggering, a little bit hard to comprehend, and maybe a bridge too far. But it doesn't mean we're not going to try. If you put that in contrast and think about what it will take to get to your Ookla display looking a little bit like this. Well, in perspective, about a year ago, there was a big announcement with Nokia and Turkcell for a downlink speed in a commercial environment using commercial equipment. This is not in a lab, at 4.5 gigabits per second with an 800 megahertz bandwidth, which translates to 5.6 bits per second per hertz spectral efficiency. So if we want to get to higher data rates, you can see the demand on bandwidth. If we just assume a consistent spectral efficiency of 5.6 bits per second per hertz, which in the real world is pretty much unheard of for a mobile system, you can see the bandwidth demands are quite tremendous. Just simple mathematics, especially when you consider my previous point that spectral efficiency really hasn't grown much. And if you look at the map of where we've been, component carrier bandwidth versus peak theoretic data rate, you can see this line doesn't change very much. Both scales are logarithmic. There have been some improvements that have been made, but in all the packet radio systems that have existed all the way back since 1G with CDPD, we're still looking at kind of a line that doesn't vary much. And we might make some significant improvements, but if you think about that, if you go to, let's say, you double that spectral efficiency, you're still looking at 90 gigahertz of bandwidth for a single link. Pretty substantial, right? And then if you look at the allocations, and this color coding here is probably going to frustrate some people here. I was trying to map this with respect to some of the issues. Let me go back here and open up my chat so I can see what's going on here. Just a couple of things to highlight here in terms of the spectrum allocations above 100 gigahertz. First of all, just about all of it is shared. There's multiple allocations if you wade through all the regulatory stuff. And I spent a fair amount of time with the ITU documents over the last few days. And the other thing to highlight here, I just picked one example, radio astronomy, because I know that was a driver for some of why these questions came up. And radio astronomy presents kind of a unique case of coexistence because it's not a coherent signal. You've got Doppler shift, which means that the spectrum that you have to worry about is way broader than a particular spectral line or something like that. It's quite complex. But everything I have in italics is on the left side is a shared resource with radio astronomy, among other things, right? There's Earth observation satellites and other things, but this is something that's shared with radio astronomy, which has particularly sensitive receivers. And on the right side, this is the area above 275 gigahertz, and just about everything from 275 to 450 also is set aside by the ITU for our radio astronomy, again, as a shared resource, except for the bands that I have highlighted. So you can kind of see on the right side what's going on. And then, below 330 gigahertz, contiguous bandwidth of greater than 10 gigahertz is available only in 6 spots. And most of those collide with other users. So coexistence is going to be very important. And the expansion of using these bands is quite a big challenge. So let's see here. So then I spoke or I wrote in the abstract about additional versus new spectrum. And some people might accuse me that these are the same thing, but I'd like to think about the words as meaning something a little bit different. It has a particular impact on us from a measurement perspective, and our customers or our users from from the perspective of people trying to make systems that work. I think of additional spectrum as spectrum that hasn't been used for mobile services, and therefore you have to think of how it is used in a specific way. Higher power levels from base stations, a lot higher density. You got all these radio transmitters and receivers, and then mobile devices transmit in all directions, right? It's very difficult to get these devices to be specific. They're not attached to the ground. People move their phones all over the place, and even if they have directional antennas, it'll point in any direction. And then almost always these days, the incumbents are affected because there's not a lot of greenfield spectrum. If you think about it from a new standpoint, these are all the technical aspects that one has to consider. Everything from passive components up to link management, mobility management, and standards, and everything in between. Materials, there's a bunch of stuff I don't have listed. So if I think about those two facets of what's going on, let's see what that looks like from the standpoint of measurement. Let me pause for just a second. Is there a precedent here in terms of answering questions at the end or during the course of the presentation? Do you have a preference?
It's up to you, Roger, if you want to take them as we go along, or, in the interests of you getting through your material, perhaps we'll take questions at the end, if that's okay with you.
Yeah, that's fine.
Okay.
If I see something that's particularly relevant, I might jump in and interrupt myself.
Absolutely.
But okay, sounds good. Thanks. So how do we think about it from a measurement perspective? From the additional perspective, additional spectrum perspective, it means we have to measure more bands. And a lot of times that has to happen in a single chassis or a single solution. And that's characteristic of what our customers or researchers have to do as well. The number of frequency bands you have to put into devices these days is quite large, and that makes them complex. And because of the way that spectrum policy is developed and it's all chopped up into pieces that are scattered all over the place, it drives a significant amount of challenge in the technical arena. We also have to measure the compatibility and the coexistence, and not just in the open space, but also within the chassis. How do people keep the signals from interfering with each other within the device they're designing or making or whatever? And that ends up being somewhat more interesting than you might imagine. And then obviously there are regulatory and policy requirements, standards requirements that get added that place demands on how we design what we do. And then just like all of you, we then have to research the technology to enable these measurements. We tend to have to be better than the device under the test, although not always. But in terms of power, sensitivity, integrity, speed, and we tend to have to be slightly ahead of policy and standards so that people can develop things prior to when the standards become manifest. And we not just have to measure performance, but also the functional capabilities, and in some cases, capabilities that are you might even consider a little bit more subjective, quality of service and higher up. So we have to think about things in this perspective. And when I talk about trying to do things from a practical and affordable standpoint, well, this is a system for millimeter wave, somewhere around 28 gigahertz, for making measurements on digital pre-distortion for power amplifiers. And so practical and inexpensive is probably not how I would define this, but for early development, this is the kind of thing you have to have. And it becomes super important that this become somewhat more, I suppose, integrated, easier to use, and systematic as the technology matures. So that's the challenge that we have to maintain. So why do we measure all of that? Well, you have to think about, if you're going to do communications at these bands, what does it take to get from the transmitter to the receiver? And have here some information from a paper that came out about a year and a half ago. It was a link budget analysis, and this was all done from the standpoint of, it was all simulation. There wasn't a specific set of measurements made, but simulation is really where it starts. And this is pretty simple. It's a pretty high frequency at 300 gigahertz with a 10 meter distance between transmitter and receiver. And think about this in terms of a mobile application access. So you can see the specs here, but I'll highlight a couple of things that come out. First of all, The power amplifier on the transmitters at 13 and 5 dBm, downlink and uplink respectively, those are not super high from the standpoint of communications. And therefore, we have these in this model, an aggregate antenna gain of 60 dBi in order to maintain a decent link, so we can get about 17 dB signal to noise ratio. That means very high gain and very directive beams, and therefore you have to reallocate the beam every 3.6 meters as you move in a lateral basis from this 10-meter distance. This all requires a noise figure of 15 dB or better, an aggregate noise figure at the receiver. And that's pretty much the state of the art as of a couple of years ago from the standpoint of low noise amplifier receiver systems. So kind of pushing at the very edge, what I describe here is the way we think about a link budget in a communication system. Many of you already know this, but what this drives is all the work that has to be done to measure how well the system is going to manage a link in this case. And it's going to look different for different path lengths and different frequencies and different signal and noise ratios and data rate expectations. But the point is we have to think about all this and put the numbers on it. So the measurement challenges, I say, boil down into three areas. First of all, we have higher frequencies, and that drives higher bandwidths. The second thing is since we get to these higher frequencies, the systems that operate, the radio systems, are much more highly integrated, and therefore they operate as a system, and they have to be tested as a system as opposed to testing individual components. And this adds an extra piece of complexity. And because of the antenna gain in these systems, now we're doing testing and deployment in 3 dimensions. And obviously that has to be done in something that is becomes more mainstream. So if we first think about power, and this is just a simple example of, let's say we have a calibrated signal source that's a piece of measurement equipment and a device we're trying to test. We're trying to test its receiver. And if you just look at what you have to deal with to get the right amount of signal to the low noise amplifier with a high enough integrity, the demands are quite substantial if you think about making a link here with an antenna rather than a cable. And the power turns out to be a super important issue in everything. If you want to have a better link budget, you have to have more power. Generally, that's what you want. That causes other problems, but you have to have enough to excite the device under test. I have to have headroom because most modulation in communications is a complex modulation. And so the peak to average power ratio gets you in trouble in terms of linearity. There's a lot we have to do to extend the calibration plane to the device under test, so we know exactly what the measurements are. And power is almost always means heat. And so managing that heat issue is kind of a big deal. And if we dive a step further into just the power and look at the state of the art for saturated output power versus frequency in various semiconductor technologies, this is a great thing that's put together by Georgia Tech. They do this summary all the time. It's a really cool spreadsheet that has all this information in it. Kind of gives you an idea of where things are at based on a meta study that they continue to do. I really admire this work. It also makes for great slides. But, for indium phosphide, sort of the shining star of carrier mobility and the band gap at 140 gigahertz, maybe 25 dBm at best, and that's coming right off the chip, and maybe 20 at 300 gigahertz. So these are not super massive power levels for managing communication links. And then from the standpoint of efficiency of these systems, at 25 dBm, you're at 10% above 100 gigahertz. So a single stage is going to generate something like 3 watts, and that's just the power amplifier. So there's a lot to do to manage how much heat is going to come out of this system. And it's also an energy efficiency issue for how we want to maintain a system that is sustainable. So these are some pretty substantial research challenges that we all have in front of us. And our job is to help with some of that, but we have to manage this as well because of the way we have to manage the measurement equipment we have. Then in terms of signal integrity, the standard way to measure this in a modulated system is with error vector magnitude. And so that is the aggregate or the average magnitude of an error vector that is between the ideal point on a constellation diagram and where the signal actually is. And when you think about so I talked about power management and linearity limited issues, and that's on the right-hand side of this graph, but the error vector magnitude goes up as you get to lower power levels because of aggregate phase noise, particularly in complex modulation. And the error vector magnitude is a integration of the subcarrier signal sideband phase noise across that entire bandwidth. Well, the FR2 requirements we had in 24 to 52 gigahertz, typically they asked us, all of our customers asked us to have at least minus 40 dBc, so about 1% EVM for our system. It had to be significantly better than the device under test so as to make that measurement feasible. What's interesting is that we're getting a lot of the same kind of requests today for frequencies and bandwidths that are significantly higher. This is only a little bit of an exaggeration. And as I'll highlight here that the integration up there is over the entire bandwidth. So as you know, as you get to higher bandwidth, you get noise power, but then in this case, it's the subcarrier phase noise on each one of the subcarriers spread out there. And that can make things quite challenging. So the demands we have on our systems for noise, modulation integrity are quite substantial. And then we have big bandwidths. So there's lots of high speed digital to analog conversion and digital signal processing that happens. And once again, from looking at a list of state of the art for analog to digital conversion and the power efficiencies, I just did a quick analysis here. So 15 gigahertz of information bandwidth and a 10-bit effective number of bits. So that's maybe bigger than what's necessary, but I just picked a number here. And we're looking at 40 gigasample per second and about a 50 watt consumption for a single analog to digital converter. Not very practical for a mobile device, right? And then, the state of the art, I don't mean to make this a Keysight advertisement. This is a pretty cool box, but the point is that, we have a system here that has 256 gigasamples per second. It's a 10-bit ADC. So that's the effective number of bits. It's a little bit smaller than that, but it uses 2,600 watts for when you got all 4 channels fired up. So that's also not very practical in a base station or in a mobile device, clearly, because it's also quite heavy and large. But the point is we have a ways to go to be able to get our signal processing to handle bandwidths like this in any kind of a sustainable way that will not use up all your battery or all your money or all your resources on the planet. So the next challenge we have is measuring the device under test as a system. Most of us in the measurement world are trained to build individual components and measure them and see if they're okay, and then put them all together and hope that they work well. So to some extent that happens, but in a lot of cases, the integration of these systems is so tight because of the losses and with the high frequencies and very short wavelengths, the challenges of mechanical tolerances that have to be very tight. That means that you can't really put connectors in here to interface with subsegments of the system. So you can make a lot of measurements when the sole measurement interface is out there on the right. And those are down there on the lower left there, error vector magnitude and sensitivity and, antenna power and those kinds of things. But it's really difficult to get into the middle of this thing and make measurements of the figures of merit of any of those components, like the gain or noise figure, the low noise amplifiers, or even the efficiency of the antenna. And those become quite challenging. Obviously, a lot of that gets done at wafer probing, but that is a a more and more difficult way to understand whether the system is going to work simply because of the interaction of these components. And when they're all integrated together, then the modeling that has to be done ends up being more and more important. And we have to do this in our own systems as well in terms of managing and measuring how well our systems work. So this ends up being a problem and a significant challenge for us. And nowhere more manifest than in having to make measurements over the air when you have your only interface to the device under test as an antenna. And an over-the-air measurement means that you have a radio solution making measurements on one side, a device under test that you typically put inside of a chamber, a probe antenna. You have to move that device under test around with a positioner. Sometimes you move the probe antenna, but the idea is you're making measurements in three dimensions. You have to control all that stuff with software. So that's the basics of an over-the-air system. Inside of that chamber is an area where you specify the behavior of the electromagnetic wave that we call the quiet zone. And you also have to maintain a certain distance between the antenna probe and the device under test. Typically a far field, although that's not necessary in all cases, but we have to make sure that the phase and amplitude of these waves is well behaved. And generally the preference at these frequencies is to make far field measurements. And that far field is, as most of you probably know, is a function of the diameter of the antenna aperture and the wavelength. And just to illustrate some of the challenges here, as you get to a larger antenna aperture, which is one of the ways you get more gain in your antenna and hence get up to those aggregate gains that could be 40 to 60 dB, you have a larger aperture. And that means you have a larger far field distance, which means that the chamber can get quite large. If you think about 140 gigahertz system with a 10 centimeter aperture, the far field is 9 meters away. That's a big unwieldy chamber. And it also means you have 95 dB of free space path loss between the transmit and the receive, which impacts your dynamic range of your measurements. Significant measurement challenge to make all of this stuff work. Now, one way to overcome that is doing a near field to far field, or rather far field to near field translation with a parabolic reflector. And that gives you a larger quiet zone, and you can get the probe and the device under test significantly closer together. There's lots of presentations on this capability, but effectively you put one of these things in a shielded enclosure where the probe antenna down there mounted to the floor is at the focus of that parabolic reflector. The device under test is on the 2-axis positioner there in the foreground, and everything's boxed up inside of a chamber to keep out the unwanted signals, to keep the signals inside the system from getting out, interfering with somebody else. And to drive very specific behavior of the radio waves inside the box. But these are complicated. You might say, well, there's a probe antenna, there's a positioner. That's pretty simple, 2-axis robot and reflector and some foam all inside of a tin box. And it turns out that it isn't that simple, because the probe antennas are narrow band if you want reasonable gain and reasonable accuracy and behavior. And so we have to make conformance test measurements even in the 28 to 52 gigahertz area. So we're not even into the sub-terahertz space yet. But as an example for 5G conformance, we have to make spurious measurements from 6 gigahertz up to 110 gigahertz. And so you can't do that with a single probe antenna. And so we put 5 of them in the base of our chamber, switch between them depending on what band we're in. We also have to maintain links with the device under test. In this case, it's a mobile phone. And so there are additional antennas inside the system to maintain a link. The FR1 link antenna is because the system requires that to maintain a link for making measurements. The FR2 link antenna is to cause the beam to be pointed in a direction that is not necessarily at the reflector and the probe antennas in order to make TRP measurements and do beam peak searching and that sort of thing. So these become quite a bit more complex. And then the chamber has to be isolated. Because you have a link at FR1, you now have to have isolation from about 450 megahertz up to 200 gigahertz and somewhat more than 75 dB across that entire band. And so that's 75 dB inside of a chamber may not seem like it's very difficult, but across that frequency band, it ends up being quite challenging because you have to ventilate the chamber and have doors on it and bulkheads with cables being fed through and so forth. So this ends up being somewhat more difficult. And then we have to maintain temperature. So not only an anechoic chamber, but also a thermal chamber to manage. We put this bubble and have a temperature control unit to manage the temperature inside the bubble. And the bubble is made of a foam material that has a low epsilon, a low delta, to be as transparent as possible to the radio waves in question. And then obviously, since we have all those different probe antennas, we have to have calibration through multiple paths and multiple frequencies. So pretty big system off to one side. So it becomes quite a bit more complex because we're making measurements in 3 dimensions. And somebody decided we needed to make those measurements at different temperatures. Not only that, we have to consider things like polarization. So most of these systems use a 2x2 MIMO based on vertical and horizontal polarization. That is a polarization that is not supposed to be known in the device under test. You don't know that in advance what the polarization is, so you have to find it. And that means there's a roll mechanism on the antenna, which is in this case a dual polarized antenna, the probe antenna, to rotate it so you can find the peak polarization. And then you can see on the right side more complexity where those 5 antennas are down there in the lower left of that photograph near the, facing the parabolic reflector. And there's, most of you will be able to tell me that in a paraboloid, there's only a single point of a focus and there's 5 antennas. And so there's something you have to do to make up for the fact that not every one of those antennas is sitting in the focus. And there's a mathematical compensation that has to be made. It does have errors associated with it, but that's one of the more practical ways to do this. So it's a description of the complexity here. And that's just a taste in that. So the next question is, well, why do we need a license? Roger, you just discussed all of this stuff about, putting these things inside of chambers. And so if you keep them enclosed in an anechoic chamber, you don't really need a broadcasting license. And that is true. And most of the work we do is indoors and in chambers, and that's for a whole bunch of reasons. But we do have to operate within the regulatory requirements, and we have to help our customers do the same. And some of the things we do are outside of the chambers. We're not going to build a big communication system with base stations and that sort of thing, or at least right now we don't have plans to. But occasionally the measurements are made outside of chambers, and it's important to stay within the regulatory limits. And those locations there up in the upper right, that's really serves the critical mass of the people that we have working on this, the technology experts. And it really gives us the flexibility to address a wider range. The Spectrum Horizons license isn't the only one we have. That's the one that was granted in January. We have another one that was granted last June that covers the somewhat more modest frequencies from 93 to 240 gigahertz in various bands. And the point here is, if we're going to specialize in helping people make measurements to explore these areas, this is an important place for us to operate. So I'll quickly get through a little bit with respect to coexistence. There's a myriad issues here with coexistence, and we're involved in many of them. And just as an example of some of the things that have to be done, in the early days of 5G, there was a lot of talk about filtered OFDM, various forms of filtering on OFDM to get rid of the spectral splatter that is so characteristic of LTE, which you can kind of see in this middle picture here. And one of the alternatives was this filter bank multi-carrier approach. So you could notch a filter bank multi-carrier and stick an LTE signal in the middle of it, like here on the right. And then as the closer you get those filters to the LTE signal, you can see how the EVM gets higher. So this is a way of measuring how sensitive the whole system is to the number of subcarriers you've allowed in your FBMC signal and how close they get to the LTE that we just stuck in the middle of this. Now, it turns out that FBMC wasn't a good solution because it looks really good on paper, but when you put it through a real system with real phase noise and real nonlinear amplifiers, it doesn't perform a lot better than LTE or a traditional CPO FDM signal. And you can see a bit of evidence in this one. So here's a different analysis that says, well, okay, so we've moved our filter bank such that we can put the LTE in the middle of it and everything is fine. But if I have, if my power amplifier has 3 dB lower in its compression point, you can see the error vector magnitude increase significantly, and you get maybe 5 dB closer to the carrier in terms of your error vector magnitude. So that's another thing you look at in coexistence, is not just how close am I, but how good is my radio? How well is my radio performing in terms of what it's supposed to? And there's a million things you could look at in this space, but you can see the distance that becomes a little bit more obvious when I circle those here in this analysis. Another case, and again, we're in these modest bands in the FR1, below 7 gigahertz area, but this translates to other bands as well. So in this case, it's an analysis of LTE versus an S-band radar. In the upper left, the pair of signals is, or the pair of pictures is the same signal, but just the right-hand side there is zoomed in a little bit. So with 100 megahertz separation between the center of these two carriers, you have a reasonable EVM, reasonable performance of LTE. But if you move 50 megahertz closer, so there's only a 50 megahertz separation, the EVM becomes 14%, is pretty much unacceptable for a reasonable LTE signal. So that's another one, is how close is your neighbor to you? And another example of that would be for satellite, looking at OFDM versus a satellite signal here. And the closer we get, and this is actually at a 28 gigahertz space. And you can see in the upper part, just the depiction of two different signals that get closer together in frequency and how they start to overlap in their bands. And that's illustrated in this EVM versus subcarrier plot. So as you get close to the band edge, which is in the right-hand side of that, you can see the error vector magnitude creeping up because there's more signal that's interfering. So I'll end it there. Give us a little bit of time for Q&A here, and just close with one of my favorite comments. I had a boss that handed out what he called the Kelvin Award about every month when I first started at Hewlett Packard. And that was for somebody that could actually take a phenomenon and put it into numbers and measure it. And to some extent, this is why, Keysight is in business, right? We sell things so people can measure things. But the real point I want to make here is that when we, part of why we're investing in all this area is to take advantage of the spectrum, but knowing that there's other people that are going to use it and different means of using it. We can't really understand how shareable things are without putting numbers of those and making those measurements. And that's sort of what we do. And so that's why we're investing in this area, why we have licenses to operate in this area, so that we can understand more about it and help that process. And with that, I'll end, and I can just go through the questions, if that makes sense, in chat.
I think that's fine. And the people who ask the questions, if you want to unmute and ask them, that's okay too.
Okay.
So Russ, do you want to go ahead and ask your questions? I think they're very similar, so you can maybe combine them into one.
Sure. So I was early on when you went over your spectrum history slide, you had this very large forecast of 100,000 megahertz, which seems a bit high compared to past spectrum demands. And I'm just wondering if some of that's going to be addressed through edge capabilities, compute throughout the network that could reduce that that requirement for spectrum? And then the second part of this question is, what about the expected gains in efficiency to reduce some of these needs as well? And I think you covered a couple things there and some of the challenges, but just wanted to get your thoughts on those two.
Yeah, so it should, from my perspective, if you look at, if we really do build a system where you could expect a user data rate, a user experience data rate to be tens of gigabits per second, the spectrum demand is huge on that without making big improvements in spectral efficiency. So they're either direct improvements in terms of work for improving number of bits per symbol, or some sort of encoding capabilities, or literally making the cells smaller, or indirect improvements, as you suggest, which would be leveraging edge capabilities. So an example of that would be predictive technology, maybe even using artificial intelligence to derive a system to make smarter decisions as opposed to brute force decisions for what's going on. In a lot of cases, I think Manisha will tell you, we don't have a very efficient use of spectrum. I mean, even if your specific modulation format has decent spectral efficiency, it's not used as well as it could be. In other cases, it's grossly overcrowded. But I think a smarter programmable system can be leveraged to make an effective gain in efficiency and better use of the spectrum without any question. And I do, the 100,000 megahertz gain is rather substantial. And I guess I would say, well, maybe that's over the top, but I was kind of blown away back in 2013, 2014, when they were talking about adding what they were for 5G, which if you just expand that graph that I did and look only at 5G, it's many times that we added for any previous generation. And so it's probably indicative of exponential growth in use.
Thank you. By the way, great presentation, great slides. Hopefully you share the material.
Yeah, I think that shouldn't be a problem. I'll send this to Manisha and Dean and make sure we've got, or Nick, and make sure that's handled. Okay.
Thanks, Russ. Nick, you're up next.
Wow, that was quick. So I wanted to make sure I understood one of your slides where you showed spectral efficiency. Were you assuming that spectral efficiency was roughly the same as we go up in frequency, or my gut would be that it might actually go down in terms of spectral efficiency as we go up in terms of center frequency?
Well, it can go down, partly because of the challenges of complex modulation at the higher bands and that sort of thing. I think the graph that I was showing had more to do with historically what the system expectation was of the peak theoretical data rate versus the component carrier bandwidth. And that what had happened is, we saw, growing bandwidth, but the slope of the line didn't change much, right? I don't think that we were making great improvements in spectral efficiency. We might have gotten a little bit better with 5G from 4G, but it's still in the 1 to 2 bit per second per hertz area, just in general, based on the research that I've read. So I think we're going to have to get way better with efficiency at the lower bands. And as we move into the higher bands, obviously the first cut at that is going to be fairly inefficient and will improve as technology goes on.
But Roger, on that, the spectral efficiency, I agree, has not changed much, but all of the massive MIMO and beamforming capability allows us to support more users with the same spectral efficiency. So the net bits per second per area, per hertz per area, I think has gone up. Would you agree?
Absolutely. And that's my point too, with spectral efficiency as a function of use on square meter has definitely improved. Most of that gain has come from making the cell smaller, but some of the more recent work that's been done with advanced beamforming techniques has made a difference. And I think we can expect to see that to continue.
Mike, you had two questions. Would you be able to combine them into one short one that he could answer? We have a bunch of questions lined up for Roger.
Thank you. There was the speaker commented about radio astronomy. I think maybe it's because he's more familiar with it. As it turns out, for the sharing issue, it's not radio astronomy. While there is radio astronomy, in reality, the radio astronomy tends to be in obscure places. The real problem is passive satellites. And the problem with passive satellites is really the issue of high elevation angle side lobes from 6G systems. So if you want to share with passive satellites, you have to figure out ways to decrease your high elevation angle side lobes. Not impossible, but NASA likes to think it is impossible, and therefore NASA likes to create problems. But the focus, the real sharing problem is the passive satellite one, not the radio astronomy one. Thank you.
Thanks, Mike. I appreciate that. And yeah, that was one of the things that that slide that I showed is something that I stole from one of my colleagues, Greg Jew. And in particular, he was highlighting some of the areas where they specifically haul out the WESS issues as being as one of those. So, yep, I understand that. Thanks.
Okay, next up is Kumar.
Yeah, so Roger, hi. Good talk, by the way. The question I had was regarding the accuracy to which you have to specify components as you go up in frequency, both for practical systems as well as for test equipment. And there's actually a second part to this that I thought you could comment on that regards your thoughts on over-the-air testing, especially as we go to larger antenna arrays. What can be done to make the over-the-air aspects a lot easier?
Yeah. So for the first question, the tolerances, there's kind of two things you have to look at here. As you get to the higher frequencies, the mechanical tolerances on these devices become exquisitely difficult to measure and maintain, just because the shorter wavelength, your wavelengths are now getting closer to the same size as the mechanical features, and so there is a tremendous amount of precision that's required in the mechanical tolerances. From the standpoint of the electrical behavior, is it tighter than it is at lower frequencies? I don't know that I would say that. I would just say that we have the same kinds of issues we have to deal with in terms of trying to get as low in noise, high linearity, and many of the other things out of these systems. So I would say it's more challenging because we haven't spent as much time at these frequencies, right? They're not as mature from a technology standpoint. So there's a lot more work that has to be done. And certainly from a mass production standpoint, it becomes quite a bit more challenging. A lot of benefit you get from that perspective is the economy of scale that comes from what happens when it goes mainstream. And then from the standpoint of OTA, this is a big challenge for us, right? How do you get OTA to be such that it's fast and it's easy for the more casual user? 10 years ago, there's probably less than 2,000 people in the world that understood how to make measurements in an anechoic chamber. And today we have hundreds more of engineers that are doing development in FR2 systems and now in greater than 100 gigahertz systems, because this is becoming more mainstream. And we have to find ways to make that more accessible. And if I told you all the ways that we're looking at that, I would just give away our roadmap, and that probably wouldn't be very, my boss wouldn't be very happy about that. But suffice to say that that's right on the edge of my mind, having managed the OTA R&D team here in Santa Rosa for a few years. and what the challenges are. And the way I like to look at it is we have to make this, we have to do for this what, like the 8510 did for vector network analysis, right? We have to take something that used to be exquisitely difficult and make it much more straightforward and cheaper.
Yeah, I would imagine that even outside of an anechoic chamber, there are some uses that you could maybe imagine OTA testing to be suitable for, especially even with the C-band. There are many interference scenarios where it would be useful, for instance, to be able to measure, make field measurements of radiated energy.
Yeah, absolutely. And then the field measurements end up being challenges because over the air measurements when you're outdoors then bring with them another set of issues. But that's exactly right.
Yeah.
So I think we may have time to take a couple more questions. Vijay, you want to go ahead and ask yours?
Yeah, hi. Yeah, thank you for this excellent talk. So the question that I have is about polarimetry. I saw you had a few slides dedicated to dual polarization at terahertz. And what I want to know is there any difficulty or challenge in applying polarimetry at terahertz compared to millimeter wave or other frequencies? Because this OMT switch that you mentioned in some of the radar applications, especially weather radar, it has been used at S-band, C-band, sub 6 gigahertz frequency. So what is the challenge here?
So there's a significant challenge in that if we're going to make measurements in this space and you want a single dual polarized antenna, I have yet to find an OMT that operates above 100 gigahertz for sale from anybody. It's not the sort of thing I can just buy off the shelf. As an example, right? I'm sure they exist, but they're probably custom made and in laboratories in various places. But that's one primary issue, which means that you have to have a separate antenna, a different polarization, and ensure that it has the right rejection of the other pole. So that remains a challenge and is going to take some work as well. Most of the systems we see people working on now, they are still considering dual polarization simply to get better efficiency of the spectrum, right? If you can manage a MIMO system one way or the other, and you've got the possibility of orthogonal means, then take advantage of it. So that's a priority. It's just that's the fact that I can't go down to Radio Shack and buy a 140 gigahertz OMT is a pretty big deal. So that's one of the things we're going to have to work on.
I see. Thank you.
So we have a number of other questions. We are at time. If I want to be respectful of your time, Roger, would you mind taking a couple more, or we can have them?
I have time to take a couple more, and if there's any left when everyone gets bored and leaves, then I can also just, if you get me a transcript, I can write some answers out as well. But I've got time.
Okay, so why don't we go to something that's maybe a little bit stir up the pot a bit. Ganesh, you had a question. Did you want to ask that?
There was a comment on what Michael Marcus had mentioned. He said there is no facilities exist out of east of Mississippi over 100 gigahertz, but I'm at MIT's Haystack Observatory, and we have a 37-meter radio telescope. It's a receivers up to 116 gigahertz, and then we have plans to go up to 230 gigahertz. So all these systems will need to coordinate.
Well, we have the makings of a perfect testbed right there, right? You have,
yes.
The receiver, and you have some transmitters in Northeastern University, and
that's right. And I have several of my colleagues are on this call, including the head of astronomy, Jens Kaufman. I guess you have yes questions too. I think.
Yeah, Jens, why don't you go ahead with your question?
Yeah.
Thank you.
I should ask something, but maybe let me continue on Ganesh's point that there are actually a couple of ambitious radio astronomy projects that will not necessarily be in two isolated places. So there's actually a plan of the National Radio Astronomy Observatory to spread out many telescopes in the Southwest, some of them actually across the entire continental United States. And some of those might be in relatively accessible places next to highways or so in order to service them. So that might actually become a long-term problem, that there might be spatial coexistence between people who might want to have high-speed internet and radio astronomy facilities that will notice that such signals as RFI. But let me actually make a constructive question here. I was wondering whether you have thought about how to manage the coexistence with radio astronomy long-term, for example, with having spatial exclusion zones or spectral exclusion zones that might be time-dependent. Plus, there was one other point which I forgot.
Yeah, so Jens, it's actually it's a really good question, and I have to admit that I have not thought much about this. I did get some materials on the topic to read in a lot more detail to understand it better, because there's a lot of things that I have to admit I had not thought about from the standpoint of coexistence and it goes way beyond radio astronomy, just an entire number of things. And, it started when my family started asking me about this little misunderstanding between the FAA and the FCC a few months ago. But I think what I would say is what I've read from the radio astronomy community seems like, the treatises on this that are in the context of, hey, this is a reality we have to deal with, so here's some ideas, seem to make sense to me. But I haven't thought a lot about it myself to form my own opinions on this. Right now, I'm kind of still in learning mode, so I have to admit a little bit of ignorance on this. I was, for instance, even though I'm well aware of all the issues associated with, radio astronomy and looking at far distant objects with significant redshift and differing redshift, I hadn't realized, it never came to, never thought about the fact that means that the spectrum is spread all over the place, depending on what you're looking at, just because of different speeds of items. And isolating particular bands only goes so far. There's other issues you have to deal with. And then obviously looking at the thermal situations and maybe studying dark matter ends up being that much more difficult because it's much more broadband. And I was going to make probably a future slide on this. We were making jokes at the beginning of the presentation about me playing the saxophone in my house and how my wife's ears do not have saxophone filters on them. And it's impossible to put saxophone filters on her ears because she has to listen to the same bands that I speak in, and that's pretty much the same frequencies. But the saxophone is a lot louder than she would like it to be. And there's really no way to filter that out. And so we have to make for some kind of an arrangement, which in some cases is time-based. In other cases, I try to put myself in an anechoic chamber. But there's a lot of parallels on this whole thing, and I just have to think about this a little bit more to establish a more useful answer to your question.
It's actually worse than just having redshift or so, because some of our signals are truly broadband.
Yes.
Yeah. So in case that is of interest to you, of course, one question, as you said, your company is into measurement. So that might be something we might be interested in on the long term, to assist with measurements on how do you actually characterize the impact of future systems on radio astronomy.
So that's something that I like to encourage more than anything, because there's it'd be nice if there was just no interference at all, but that doesn't work for anybody based on the global use of the spectrum. And so understanding it and measuring what works and what might not, and where the issues really are, and being able to put numbers on it is a pretty important thing. So I'm certainly intrigued by that, and definitely will take you up on the offer.
So I think in the interest of time, we will close the lecture here. I know there's some outstanding questions, and please, I'm sure Roger will be happy to answer them offline. And I really thank you so much, Roger, for coming to SpectrumX and for starting this dialogue. I think the fact that there are folks that are willing to work with you on measurements, trying to identify what interference in these bands look like. Nobody has done these kind of studies before. So I do hope that there will be follow-on between members of SpectrumX and others on the call and Keysight, and we continue to push the spectrum boundaries into the frontiers and maybe even beyond. So thank you again very much, and thank you all for coming.